Hello, everybody. This is Jing Chen. I'm going to tell you about Algorand's consensus and smart contracts. Peter already said I'm the chief scientist of Algorand and co-author of the consensus protocol. I'm at Stony Brook University. Now I'm on leave from Stony Brook and working full-time at Algorand. A little bit about Algorand. It means two things. One, it means our consensus protocol, which is Byzantine agreement, based on Byzantine agreement, and I'll tell you more about it today. And also, it means as a product, it is a public blockchain network. It launched last June and has been there ever since. We'd like to consider Algorand as alternative public blockchain because it wasn't a hard fork of any existing solution before us, and we developed it from scratch and based on first principles with worst case analysis and rigorous mathematical proofs and so on. Now, as promised, today we have two big sections in the lecture. One is about the permissionless consensus protocol, and one is about Algorand smart contracts. Currently, I'm leading the team of the smart contracts, so that's my new focus after the consensus. Okay, before we dive into the technical materials, let's build some common language together. Distributed ledger, you should know it by now. A sequence of transactions organized in blocks. And the later block would contain the hash of the former block so that there is a proper order of the blocks and nobody can alter the content. Hence the name, the blockchain. It looks like they're chained up. Now, what are the properties that people are shooting for a public ledger? We want it to be readable by all and writable by all. All not just mean people, all people in the school, but all really means people on the entire internet. It's a permissionless world, and everybody is able to read and contribute toward deciding what the next block should be. Tamper-proof for all means that the block, once generated, the content cannot be altered. But if you only care about those three properties, some of you may realize that we can achieve them by a centralized database as well. That there is a central manager, and the manager take reading and writing requests from clients. We could make the central management sufficiently secure so that nobody can break into it. However, centralized management has turned out to be, in the past, often the point of failure or become the bottleneck of the entire system, has a lot of congestion and so on and so forth. So a big difference blockchain is bring to us is we're achieving all of above, but without centralized management. So it is a highly distributed system we're talking about. And such a distributed ledger, if properly implemented, is good for a lot of things. For example, notarization and storage. People can put their evidences, documents, copyrights on the blockchain, and nobody will be able to alter that. Actually, there have already been law suits where the court ruled according to evidences preserved on the blockchain. And it can serve as virtual trust party so that different people from different corners of the world will be able to trade with each other via the blockchain without ever meeting and trusting each other. And of course, settling payments and cryptocurrencies. Maybe one day blockchain will help us cure COVID-19, who knows? All right. In terms of course, that's a dream infrastructure, but of course, the key question is how to implement it. There are a few cryptography tools I believe you have seen them during the class or in other places when you read about the blockchain. There are many cryptography primitives. I'm only going to tell you the two very basic ones a little bit. The first is digital signature, a public key and a secret key. The signer will generate a signature using his secret key. the magic is that the verifier will be able to verify the signature is properly generated for that message without ever seeing the secret key. That is by only using the public key. So only player I can generate the signature, but everybody can verify because the public key is known to all. And the hash function. A hash function is a map from a string of arbitrary length to a fixed length. For example, 256 bits or 512 bits, SHA-5, SHA-2, and so on. In the theoretical model, a hash is often modeled as a random oracle, means that the image is a random is a random string. And it's hard to find collisions which are two pre-images having the same hash image. This is a very, very crash course about, signatures and hash, but this is all you need to know in order to understand what I'm going to talk next. Okay, we have maybe 2,000 blockchain projects now if you Google. But it's sort of blockchain's open secret that people talk about aspirations a lot. But when it comes to the real technology, it's far, far away from achieving the promises. And people even famously claimed there is a trilemma that one cannot hope to achieve security, performance, and decentralization at the same time for blockchain. Fortunately, that's not a provable impossibility result. It's just a way people use to exaggerate, to emphasize how difficult it is to get the technology right. Okay, there are many existing approaches you may already heard, proof of work, proof of stake, which include, say, delegated proof of stake, where a few, say, 21 supernodes are selected and they would vote on behalf of everybody in the system. And bonded proof of stake, which means that users will need to lock up their tokens in the system without touching. And if the system ever causes them wrongdoing, then the tokens will be forfeited. So that means that security is provided via economic ways, not really via cryptography ways, as we'd like to do in worst case analysis. So Algorand's approach is proof stake, but we consider it as really the pure form of proof stake, means the following, that there's no punishment needed. We prove that the system is secure mathematically, and we do not need to forfeit people's money, even somebody is, say, double signing, because that he cannot break the system anyway. And we do not let people lock up your money in your account. So a person can always spend his money if he wants to. And it's whatever he hasn't spent out will be considered as his stake in the system. And of course, there is assumption. The assumption is the majority of the token in the system for voting is in honest hands. And that would imply security, similar to Byzantine agreements you will see later. And here, there is no distinguishing, there's no miner or user, which means that anybody can decide he will be a miner or a user, and all tokens have the same voting power. Let me give you a little bit, a very high level introduction about the properties the protocol is able to achieve. It is permissionless, meaning that every user is able to register a key and have an account in the system and participate in the consensus. It is secure against a dynamic adversary, which this I'm going to talk more in a minute. A dynamic adversary is a very strong model that in cryptography we use to analyze such protocols. It works by having ever-changing and randomly selected committees. When a user is selected, all he needs to do is to send a short message, a very quick step. There's no common clocks, which is important. Common clock is a typical tool when designing Byzantine agreement. That is a synchronous model. That is the model is synchronized, and that would be that won't be very realistic in reality. That you would see very few real systems can afford to have real synchrony. Now, the properties we achieve in terms of safety and liveness are safety is anonymous. It is asynchronous, means that no matter how the adversary can do, he can attack the protocol, he can attack the network, delay messages, and so on. He's not going to fork the blockchain. Liveness is achieved when messages are propagated within known time bound. Uh, there is no strong impossibility result in the theory literature that you cannot hope to achieve safety and liveness both in an asynchronous way. So because blockchain is going to be in charge of billions of dollars of financial assets, we choose to achieve asynchronous safety. That's a very strong guarantee. And then we achieve liveness when there is a bound for message delivery. Okay, now let's dive into the technique a little bit more carefully. You're not going to see the exact code of the consensus protocol. That would be pretty tedious proofs and protocol to go through in a lecture. What you are going to see is a bunch of key ideas in the protocol that eventually make it work. So I think those key ideas are really the important stuff I'd like to communicate. So I'm emphasizing the word chain. You'll see why in a minute. The way Algorand generate blocks are really a very lightweighted computation. There is no mining. You don't need to solve cryptographic puzzles. It's really one-on-one and sequentially one block after another. So it is a chain. But this is not, I mean, having a chain is not something we should take as given, because if you think about the data structure of Bitcoin, you would realize that even though we call it a blockchain, it's not really a chain. Most time or always, it is a tree with many branches. Because there are many people who are mining, doing their individual work without knowing about the others. Therefore, it's possible that two blocks are generated, and then users will mine, continue on the longest chain, and maybe after 5 or 6 blocks, you would be fairly certain that B1 now is final with a high probability, and so on and so forth. And instead on Algorand, that's not needed, since it is really a chain. There's no soft fork and there's no proof work. What we gain by getting rid of those two? Well, there are a few neat properties that are good to have. First of all, without soft fork, that means that we have immediate transaction finality. That a transaction does not need to wait for 6 blocks, for example, in order to be considered sufficiently final. A user can immediately depend on it the moment you see it appears on the blockchain. And without proof of work, it is really easy for people to participate in a consensus protocol. For example, like I do not buy special hardware. I basically use my own laptop to run a node. That's enough. Okay, now a little bit about Byzantine Agreement. It's a communication protocol that when the majority of the players are honest, guarantees two very good properties. By the way, there is a rich literature about the Byzantine agreements in distributed computation. It's a very critical component in the theory of computation. So the first property is called agreement. Instead of giving you complicated mathematical formulas, I think pictorially it is very intuitive, very easy to understand. A bunch of users, some are honest, some are malicious. I hope the pictures are self-explanatory enough that you know who is honest, who is malicious. They start with private values. The private values may or may not be the same. After those users communicate, honest users follow the communication rules, malicious users can do whatever they want. But after the communication, honest users will all output a common value. In the blockchain language, you can imagine that means that they have decided what is the content of the next block. There is another very neat property, which is consistency. Consistency means the following, that Byzantine agreement never try to waste people's energy and force them to achieve on something different than what they already have. Meaning that if the system starts, honest users already have the same value to begin with, then after they communicate, they will still end up outputting the same message. So that would be consistency. And in the blockchain world, that means that agreement will give you the safety of the blockchain, and consistency give you liveness of the blockchain. Cool. To summarize, it's a protocol to achieve consensus when the majority of players are honest. I put a star at majority because there are, in the literature, there are all kinds of majority assumptions imposed on the designs. Uh, Most of them are two-thirds, but sometimes you see things that are not two-thirds. Okay, now at a first glance, it seems that the problem has already been solved, that all we need to do for a blockchain is to find a Byzantine agreement and have all users participate in the agreement to achieve consensus. But why it is not done yet? Because there are two real challenges that we need to solve for a permissionless blockchain. First, typical Byzantine agreement have pretty high communication and computation cost. Now, there's another star at high because what is high? In theory of computation, we consider polynomial time algorithms to be efficient. But in real world, that's simply not enough. When we're talking about the billions of users and billions of messages sending around, even quadratic computation or communication would be too much. So we need something even better. Another bigger challenge actually is that in the classic literature, Byzantine agreement is often studied in a relatively enclosed and controlled environment where the set of users, their ID, are fixed and known in advance. None of those is true in the internet because nobody knows how many IDs a real user control on the internet and which ID belong to which user. So we need to overcome those. Algorand's Byzantine agreement from efficiency-wise is pretty good. A user would send a short message per participation step, and in expectation, the protocol finishes in constant steps, even there are the proposer of the first step is malicious. I'm not going to explain exactly how the Byzantine agreement work. As I said earlier, we're going to communicate only the key ideas here. But what is a catch? Well, this is still not good enough because, again, this is still too slow to have a billion users all participating. A single user sending a single message, the network is already congested. A first idea is also very simple. How about we randomly select a subset of users to run the protocol? And we can do that easily if the selection is public. What I mean is the following. For example, let's say we are generating block round R, and what we can do is we take the hash of a user's ID and the round number, and remember hash is random oracle, we get a random number for each user, and if we sort them, what we get is a random permutation of all the users. And let's take the first 1,000 and let them run the Byzantine agreement for BR. So we reduce from 1 billion to 1,000, which is a big improvement. Now, what's wrong with that? The problem here is that not only because we are doing public selection, not only the honest users know who is in charge, the adversary can easily decide who is in charge long before such users come into round R. So adversary would have plenty of time to corrupt such users in advance, maybe DDoS them, so that when such users are running the protocol, they are already malicious or they are already not available. Therefore, in protocols that use this approach, you typically see additional assumption needed. For example, it takes adversary a long time to corrupt a user. And by the time the user is corrupted, the round he's in charge is long gone, so the adversary won't do real damage. But that is a additional assumption that we do not want to impose. And we'd like to be secure against a strong adversary. And this is a time, let me tell you a little bit about what type of adversary we are fighting against. So we allow the adversary to immediately corrupt any user he chooses. And when we say corrupt, means that once corrupted, the adversary can perfectly control and coordinate all the users, what message to send, when to send, and to whom to send, etc. And the adversary can attack both the protocol and the network. He can delay messages, hide messages, partition the network, and so on. But there's one thing we cannot allow him to do, which is the adversary cannot forge signatures, or generally speaking, the adversary cannot break modern cryptography when the schemes are properly implemented, like forge signatures or break encryption schemes. Most of the internet is based on modern cryptography, and without that, there's no network security. If you know the literature, such an adversary is referenced as a dynamic adversary. That's the adversary typically in cryptography people use to analyze blockchain protocols. So this is a very strong adversary, actually. And we're going to design our protocol to be secure against that. Okay, so here comes another key approach in our scheme that made us secure against such a dynamic adversary. We call it cryptographic self-selection. Now the key word here is self. What I mean is this. We would randomly select a small set of users, but this selection is not public. Instead, each user will secretly select himself to participate in the Byzantine agreement. He's running his own secret lottery. If he wins, he would have a lottery ticket to prove his membership. But if he does not win, then there's no way he can cheat. I'd like to draw an analog between this lottery with a physical lottery in the real world. You probably have seen those type of things. People can buy lottery tickets from a machine or from a retail store, and you show up with a lottery ticket if you win the reward, but you cannot generate lottery ticket by yourself. Now, I just said it is important that in the physical world, a user cannot generate a lottery ticket by himself, which means that in the physical world, the lottery tickets are always printed by a central company or entity, and then it is distributed to people. Why is that? Because in the physical world, if a user is able to print lottery tickets at home, then he can secretly print not one, but maybe 10,000. And he will only show up with one of them if he wins and burn the other 9,999. So we cannot allow him to do that at home. But cryptography allows us to do exactly that, which is a user, when he generates the lottery ticket at home digitally, there is only one ticket he can generate, and that will be accepted by others. If he does not win, it doesn't matter how many times he rerun the algorithm. There will still be the same lottery ticket being produced. That's the key power of the self-selection. So what do we gain by such a secret selection? There is no communication needed. Because a user just run a local algorithm on his own computer and then send out his Byzantine agreement messages if he's selected, together with his proof of membership. And no communication immediately gives us the following, that the adversary does not know who to corrupt until he sees their messages. But in the propagation network, or in the theoretical broadcast network as well, the moment he sees the Byzantine agreement message, he cannot stop it from reaching other honest users. And this user's job is done, and the adversary cannot take back his votes. Now, how do we implement the self-selection is also worth mentioning. In a shorthand, in a very short phrase, it's done by using unique signatures followed by a hash function. Also, if some people know, this is also called verifiable random function in the literature. I want to emphasize the word unique here. Why? Because a lot of digital signatures we see are randomized, which means that the signer has secret randomness he used, and then he generated a signature. And then the verifier verifies the signature without needing the secret randomness. If you think about it, that is exactly corresponding to letting the adversary printing his own lottery tickets as many as he wants at home. Because then in a randomized digital signature, adversary can try a random string and see if the resulting signature's hash is good enough, small enough. If not, he try another random string and another one until he find a random string together with a message would generate a signature whose hash is small enough. And nobody knows the randomness. And that would give the adversary the power of always being selected, instead of being selected according to his stake or under the desired probability. So whenever you see such a selection, people work on cryptography would realize that that is a critical security flaw in the design, that the design enforces honest user to be selected properly, but does not protect against malicious users at all. That's why it is critical to use schemes that are called unique signatures, where there is a unique, as suggested by name, for each message and a public secret key pair, there is at most one signature that would be accepted by the verification algorithm. So that's the important gadget here. And in terms of what to sign, I will skip all the details. Basically, it's enough for you to know that, let's say we are trying to generate a block BR, we would derive a random string QR, pseudo-random, uh, unpredictable, from the first BR minus one blocks. And then the user would compute his unique signature on this QR and do the hash and see if interpreted as a number between 0 and 1, whether it is less than a desired probability P. And if yes, then he participated in the agreement and send his signature as his lottery ticket, because anybody can redo the hash given the signature and the check is lower than the threshold. Okay, this is a little bit of probabilistic analysis, very, very simple. Just to give you how the probability works. Let's say we want to select 1 out of 1,000. So the probability is 1 over 1,000. This is a determined quantity, and this is a deterministic signature of the user. And the hash, as we said, is this string would be unique to I, that only him can generate. And the hash is a random function, which means that we are generating a random binary string unique to I. And Well, sure, this is a decimal point. And now we get a random and, more importantly, a uniform random string between 0 and 1. So what is the probability that a uniform distribution R is less than P? The probability is exactly P. And that shows the selection probability that a user is selected to be in a committee is exactly the desired probability. And if we set P to be 1 in 1,000, then among 1,000,000 users, we can select in expectation 1,000 committee members. Here, 1,000 is expectation. And of course, in random selection, there will always be fluctuation. The system does not need to know how many actually are selected. It only need to know that with we can do probabilistic analysis, and we only need to know that with overwhelming probability, sufficient good users are selected. Right, and if you do not know what a VRF is, that's fine, totally fine. It basically is a signature, unique signature, and the hash function combined together. Okay, are we done? We would use such a signature, such a secret selection for a Byzantine agreement. Um, but for step 1, we are perfectly secure because the adversary does not know who is in charge of step 1. But what is the catch here? Now, once he sees a message from step 1, he would know those users are in charge. So if the same users are still in charge for steps 2, 3, 4, the adversary will be able to corrupt them at that moment. And then in those future steps, we would only have malicious user in the committee, which is bad. So the secret here is that in our Byzantine agreement, there is a good property we call the user replaceability, meaning the following. Pictorially, let's say we have steps 1, 2, 3, 4, and each one of them, a set of users are selected, randomly selected, which means that there is no relationship among them. Each one of them is a random selection procedure. And this only work if the Byzantine agreement is user replaceable, meaning that it does not need the participant to maintain internal states. The message for the next step can be fully deduced from the messages publicly propagated in the network. Therefore, it does not matter that step 2, step 3 has a completely different set of users in charge. They just count the messages they receive from the network and they decide what message to send next. So more precisely, as I said, this is a random selection procedure. Therefore, different steps will even have different numbers of users. And there is no shared variables among them. The protocol does not need to know how many are selected. And that makes the protocol work crossing different steps against a dynamic adversary. Okay, at a very high level, the structure looks like this. There are two phases. The first phase is a leader propose. A random user is selected. But if you study probability theory, you know that this is expectation because each user is individually selected. We do not impose correlations among their selection. Therefore, in expectation, a few is selected and sometimes more, sometimes less, but with high probability, there is at least one. And the selected user proposes a block and propagates through the network. And then the second phase. The second phase would have more users, say 1,000, individually randomly get selected. Again, 1,000 is expectation. Sometimes it's 1,200, sometimes it's 800. And then those users would digitally sign the result, check that the proposal is valid, and propagate their digital signatures. And that when there are enough signatures accumulated, the block is certified and a new block is generated. Cool. So how are stakes work in the system? So far, we have been only talking about selection of users. Now let's look at the selection probability. The selection probability is directly proportional to the amount of tokens a user has in the system, which means that at a very high level, imagine we are not selecting user, but we are selecting tokens. Each token has its own public key and secret key and generates its own lottery. And when a token is selected, it's the user who owns the token that will do the job. And step 2 is similar. We're really selecting tokens and having the users holding them to sign the message. I didn't put the word directly here, but I'd like to emphasize the difference between directly proportional and other probabilities. If the probability favors a small stake, then the system would be vulnerable to dust attack, means that some adversary could split his account into have many accounts, and each account hold tiny stake, and in this way his selection probability will be better. On the other side, if the selection probability favors large stake, then that is how the so-called mining pool would appear, that users would collaborate, collude, and put all stakes in a big account, and that would give them higher advantage. But if the selection probability is directly proportional, then it is a tie. It really doesn't matter how the users put their tokens. Having 1,000 tokens, whether it is they are held in one account or in 1,000 accounts, would give the owner exactly the same voting power. So that is also important in a system. Cool. Those are the two basic phases of the protocol. And let's just give you a little bit of the parameters and selection criterions that we use. H is assumed honest ratio. In theory, it can be anything strictly larger than 2/3. In reality, you want to use something larger because the random selection, of course, would have statistical fluctuation. And if H is 2/3, that means that your desired committee size will tend to infinite. So you want H to be bounded away from 2/3. And N is expected committee size we want in the system. That depends on, say, network speed, for example. And in our current system, it's about 2,000. And T is a quorum threshold, which means that among the selected ones, how many would be enough to form a certificate of a block? In theory, this is 2/3. In reality, it's a bit more in order to accommodate statistical fluctuation. H and M, those are two random variables, the number of honest and malicious users in a randomly selected committee. And those are the two conditions that are used to set the parameters that given honest ratio H, we choose the expected size and the quorum so that with high probability, those two inequalities holds. Now, anybody who know chain of bonds or other type of bonds would be able to solve them and find the proper N and T to use in the system. The first inequality gives you safety. That means that even the malicious users are voting for different block double voting. They cannot manage to generate two sets of valid certificates. And the second inequality is about liveness, that there are enough honest users selected so that even if the malicious users all shirk out and do nothing, we would still have blocks generated. I'm not going to do the calculation here, but basically following this recipe, you can use Chernoff bound to compute the numbers. Okay. Well, there are many other ideas needed in the system, but I think we do not really have time to dive into all of them. But those I told you about are really the critical ones. And to summarize, oh, before we summarize, yes, there's one more thing, a small thing that I'd like to tell you quickly, which is about network partition. Nowadays, we typically imagine the internet as a cloud, right? Messages are propagated in a cloud and they reach users eventually after some delay. A network partition is costly to do for sure, but it's not impossible. uh, in particular, like large site of network partition, like somebody, if an attacker is really determined he can burn like millions of dollars, probably he would succeed in separate, say, U.S. and Russia, or China from Australia or Europe for a few days, maybe a few hours. That's very costly, but not impossible. So from a cryptography perspective, we want to do worst case analysis, and we always want to prepare ourselves for the worst that is possible. This is a good principle to have, which is if we are prepared for the worst case, then worst case is not going to happen because nobody would bother to do that. But if we are not prepared, then somebody may find the chance and actually do it. So that's really a cryptography view. When the network is partitioned, the messages will only be able to propagate within their own components. What does that mean for a blockchain? That means that an adversary can secretly have a certificate for a block that all its users are unaware of. And then he can review it when it suits him. Say when the honest user managed to generate a block by themselves, and then adversary would show this one, and now we have a fork in the system. And it's very difficult to be resilient to network partitions, and pretty much it wasn't considered by most protocols in reality. In particular, if you consider proof of work, say in Bitcoin, when the network is partitioned, the two components are unaware of each other and will continue mine their blocks individually. And we would eventually have two long branches. The moment the network is resolved, then one of the branch will have to disappear. So this would happen even if 100% of users are honest. The Algorand consensus protocol is resilient to such partition in a sense of the following, that adversary may still be able to secretly finalize a block that nobody can prevent. But what we can guarantee is that if that ever happens, then that will be the only block that will get publicly finalized. And when the network partition is resolved, then the system will recover and people would see that block. Okay, so that's a little bit about network partition. And now let's wrap up the consensus part. And then probably if there are questions, we can spend 5 minutes now. The main assumption is honest majority of money. And in terms of technical advantages, computation is really trivial. That there's no cryptographic puzzles to be solved, just some basic signing, counting votes, and verifying signatures. And since there is no need to have special hardware or burn a lot of electricity, there is a single class of users. We do not distinguish, minor or particular user. And the finality of the security probability, we choose the parameter to be 10 to the minus 18 as the probability of fork. because that is somehow we did the calculation and realize if we generate a block per second, then that probability would see one fork in the edge of the universe, and we consider that to be good enough. Scalability is also pretty good because computation is trivial and the blocks are basically being generated as fast as it can be propagated, meaning that the only bottleneck in the system now is the network speed. That is from our system test. I think the longest link in the system is between Boston and Australia, which is really crossing the universe, crossing Earth. That really takes about a second to get a round trip. So that's really the bottleneck. And the speed can be easily improved when the network gets better and better. And in terms of security, it's secure against a dynamic adversary, as we mentioned before. Okay, I think this is a good time to pause and see if there are questions before we move to the next section. Are there questions?
Okay.
Yeah, thank you.
Yeah, go ahead.
Okay, yeah. Thanks for the discussion, for the presentation. There is an outstanding question in the chat room asking that if the probability of selecting not sufficiently enough correct users is considered negligible. So could you please comment on that? So what would happen if with like really low probability, we will select not that much enough honest users inside the voting committee? What will happen in this case?
Yes, probability in a system where randomness appears, of course, there is always fluctuation, and the probability of not having enough honest user is very small. But when that actually small event actually happens, the system's design is that the balloting agreement has multiple periods, and it will move to the next period and try to generate a block from that period. So it is not a constant step protocol, but it is constantly in expectation. Does that answer the question?
I believe so. I'm waiting for the commentary back inside the chat. But yeah, that sounds very good. And while we're waiting for the feedback, I have a question from my own side. So speaking of the network partitions, could you please elaborate? So publicly finalizing the block, does it mean that if somebody was able to forge a block during the partition phase, what we would save compared to the proof of work case?
Hello?
Ivan? Okay, so we have network disruptions. Look like we have a partition.
Apparently somebody is partitioning the network right now.
Yeah, so while Ivan is partitioned, actually I had also a question about partitioning. So what does it mean that you have public, it's like you have a fork, but with only one diverging block. Is this correct?
I would describe it as you would have a secret branch. The secret branch may have more than one blocks, one after another, but there won't be a second branch.
Mm-hmm. Yeah. Okay. And
So my partition is gone now.
Okay. Yeah, so,
yeah. Thanks. Yes. So continuing on my question, the question it was so this.
Okay, so
Yes?
that's a persistent partition. Yeah. Well, okay. So hopefully, well, we definitely have a partition and the fork, which is interesting. Okay. So maybe I will continue with my couple of questions. So when you talk about self-selection, so the probability of you being selected is somehow proportional to your stake. Yeah.
Yes.
So though we assume that the stake, the amount of stake the users possess, is a public knowledge.
Correct.
So the amount of stake is defined by the history of blocks agreed so far.
Yes, yes. The
Okay.
system would keep a balanced table. Yes, that's public information.
Okay. And I was a bit confused about your system model. So you said that the system is asynchronous, right? So the communication is asynchronous.
Correct.
Okay, but at the same time, you assume that a majority, or maybe more than 2/3 of stake belongs to honest users,
Correct.
right? So when you say partition, what does it mean exactly? If you say that none of the partition holds more than 2/3 of a stake, they won't be able to finalize anything, right?
Oh,
Or
the partition only applies to honest users. That's critical. Adversary control the partition. Adversary can perfectly coordinate crossing partitions.
oh, okay. Now I see. So there is a question. I think it's about the agreement protocol. What happens when at first stage a malicious player is selected to generate a block, and at the second stage the majority of the committee are malicious players?
The
Okay, I'm not sure.
first period, a malicious user is selected. Then during the first period, it depends on what he does, right? If he does things properly, um, people would achieve consensus on his block if his block is valid. But if he does something maliciously, like he may choose to send his block to some user but not somebody else, or if he generates an invalid block, then the first period will not be able to reach consensus on his block. So there won't be certificate on his block. Then the second stage, a new proposer will be selected. And the new proposer, of course, again, with some probability malicious, some probability honest. And say this user is honest and he proposed a good block, and with very small probability the committee does not have honest majority, then malicious users will shirk out, say, and not vote on it, and that will not be a certified block either. Then the system with some probability would move to the third stage. So again, this is a multi-stage, and the multi-stage it will finish with certain probability, and with high probability, it will finish in stage 1. Then if it doesn't finish in stage 1, then with the highest probability, it finishes in stage 2, and so on and so forth.
Ivan, does this answer your question?
I believe it's not my question, it's the Ivan inside the
No,
chat.
it's another Ivan. Yeah. Okay.
Ivan, you want to try?
In the meanwhile,
Maybe you
let's
can
try
go.
for the third time. Right?
Yeah.
Yeah, so speaking of the finalization thing about the publicly finalized blocks, is that true that the difference with the, let's say, Bitcoin chain would be the following? In your case, we'll be able to identify the forged block, the block which was prepared by the adversary, as early as the partition will be gone.
The question being? I think he's gone again.
Oh, this is a disaster. Yes.
Maybe we
Ongoing
should
partition.
continue, and then we can
There's
discuss
one
that
more
during
question.
discussion session.
Jing, sorry, just one question, maybe the last question before you continue, about the proof of stake in general. So if your vote is proportional to the amount of stake you have, yeah, so which means that so you receive a block rewards because your block is committed, and you get even richer. So the richer stakeholders get richer, and in the long run they would hold all the money. I don't know. So that's the question.
I think that's a misunderstanding about our system, because we do not give block rewards to the proposers. People also have that misconception. I think because Bitcoin gives the mining rewards to the miners. Algorand has a different incentive system. Um, Currently, what we do is that we give all stakeholders in the system periodic rewards and proportional to the stake. and we do not give the consensus leaders. Reason is that A, we do not want what you said. B, at different stages, like Algorand is still a new protocol, fairly new compared with Bitcoin. And our first the first goal we want is to enlarge the number of users in the system rather than reward particular consensus leaders. So therefore, as long as a user has a token in the system, he would be earning rewards proportionally.
Okay. I suggest we continue now, and if you have more questions, just keep them until the discussion. Okay.
Great. Okay. Yes. Smart consensus is one of the big things for blockchain, for sure. And I would say smart contract is another big thing. To give you some idea about current status of smart contracts values, I looked earlier that in February, the amount of assets that are locked up in smart contracts just exceeded $1 billion, which is a very high market value. Ethereum is one of the pioneers, I would say the pioneer in the blockchain world where they first developed the EVM, which is smart contract platform, together with their consensus. Their consensus is also proof of work, but their virtual machine is very powerful. It's the most popular smart contract platform right now, and it was the very first. Algorand's approach, I'd like to tell you about. It's coming from a few things that we see in the existing smart contract solutions. Sometimes we see that because smart contracts is not built into layer 1 of the blockchain, we see complicated solutions for simple problems. I'll say a little bit such as atomic swaps and other things later. Sometimes we see security flaws in smart contracts where causing people losing millions of dollars because of improperly designed smart contracts. So in Algorand approach, we have a few principles that we keep in mind, that we distinguish the solutions between on-chain and off-chain. On-chain means that it becomes part of the consensus protocol. People running consensus is also doing that. Ethereum currently has that people generating block are also working on the VM. And the off-chain side, we are going to have, so the on-chain side, we only plan to have very simple solutions for simple problems. And all the complex user-defined computation will be supported in an offline approach. And the principle here is that to keep the critical path of the blockchain short, which is an important principle in software engineering. The critical path here is, of course, block generation. Currently, the Algorand blockchain generates a block 4.5 seconds, and we're planning to further improve that. Which means that we are very cautious about putting computational logic into the critical path, because that would mean that the system would spend resource to do particular user-defined computation while everybody is slowed down. So that is important principle that we have in our design. Now, in terms of the on-chain solution, it has already been in the system since last November. And there are three things we put there for people to use. One is standard assets. This would allow anybody to issue your own token or currency or other assets in layer 1. And why I keep on emphasizing layer 1, because layer 1 has a good advantage. Being in layer 1 means that it is directly processed by the block generation logic. It's fast, and it has the same security level as the blockchain's own consensus protocol and the native token, which is Argo. So it's both fast and secure. And then we have atomic transactions and layer 1 smart contracts. I'm going to tell you a little bit next slide. The point is that in a lot of blockchain, people would have to call smart contracts in order to do them, rather than having direct logic in the consensus level. And that's what I mean by having to solve simple problems with complicated solutions. And our goal of putting atomic transactions and the layer 1 smart contracts is to make them simple and also fast. Okay, I think atomic transaction is something I want to tell you next. It should be called atomic multi-party transaction, but I'll leave the multi-party to in a second, and let's look at what does atomic mean. I believe everybody should have a intuition about what is atomicity. Atomicity means that a set of actions, they're atomic, means either all of them happen or none of them happen. There is no third possibility. Getting on the blockchain, that means that we allow multiple transactions to be grouped together. Either all of them occur on the blockchain together, or none of them do. And that would allow, well, multi-party just means the following. Multi-party just means that in those transactions grouped together, they could be issued by different users. Maybe there are 10 transactions signed by 10 users. As long as all the 10 users agree that those group need to happen together, then they can be done in that way in the blockchain. Okay, so this is about atomicity and multi-party. What can it do? There is no constraint about what a transaction in a group may do. It can do everything that the Algorand blockchain currently allows, like from simple transfer of any layer 1 currency, create an account, create currency or assets, enable account to accept new currency, include a layer 1 smart contract that I will say a little bit later, all of them. If 3 users want to make payments to each other and they want all 3 payments happen together, then they can do that. And there are many applications. One particular application I want to mention is that there is no need to use hash time logs for atomic swaps, like in other blockchains. So currently, you can look at on Ethereum in order to do atomic swaps. By the way, in case people don't know, atomic swap is exactly what I said a minute ago. Let's say Alice wants to pay some token to Bob, and in exchange, Bob wants to transfer something else to Alice. They want that, of course, both transactions occur. It cannot be that Alice transfer token to Bob first and then Bob disappear with Alice token and he does not transfer anything to Alice. That's not allowed. So atomic swap is done by smart contracts on Ethereum by leveraging hash time logs, by having one user proposing a puzzle and the other user declares tokens by revealing the puzzle solution. If you haven't seen it before, I encourage you to Google it up. I think on Wikipedia, there's a very good explanation about what atomic swap is and how it is done in hash time logs. Very, very cute and very short smart contracts. The catch is that in order to install such hash time logs in the blockchain in a secure way, the smart contracts often require time delays in how long the transaction can be considered final. And those delays are often between 24 hours and to 72 hours. That's different platforms have different parameters. But that's a very long delay in terms of finalizing a atomic swap. In using the our current atomic transactions, all it needed is the two users issue these two transactions and declare them to be in a group. And then in 4 seconds, the block will be generated and the transactions will be included there and they're considered final. The most one party can do is to refuse to sign such a group. Of course, he can always do that. But then the other user does not lose anything. The transaction, the trade simply doesn't happen, and the other party doesn't lose any token. So that's a secure way and very fast way of doing atomic swaps. I also want to mention that this is also a part of a layer 1 foundation for our off-chain smart contract that I'm going to tell you later. The off-chain smart contract solution will leverage this atomicity enforced in layer 1 to do contract state transition. Okay, now a little bit about layer 1 smart contracts. That means that this is basically a logic-driven way to approve transactions. What do I mean by this? Before, there are typically transactions are typically authorized by signatures, right? We allow single signatures, and we also allow multi-sig solutions. But now we also allow users to approve transactions via a small piece of code. If people know how Bitcoin script works, this is closer to Bitcoin script than EVM. So it is a very succinct, controlled way of approving transactions. And it basically is working around how assets and currencies can be transferred. And before transferring, the protocol will check the logic very short of script, and if the script evaluates to true, then transfer happen, and otherwise it doesn't happen. So more particularly, we installed a very simple assembler level language. We call it TEAL, transaction evaluation authorization language. It's decidable, very simple. It has about 30 opcodes. Stack language, assembly level, and we cap the script size and computation cost so that we keep layer 1 computation lightweighted. There are two ways how TEAL logic can be used to do in layer 1. Sorry, I think my battery is low. Oops. We'll see. Mm.
Okay, so something happened. Apparently, it's a battery problem. Okay.
Yeah, I believe the battery got drained.
Well, let's wait for a few seconds. Hopefully, she'll come back soon. I don't know. I don't see actually anything about the smart contracts and the references, Jinx, and I don't know if anything like this was published anywhere.
I'm not sure neither, but the thing that drawn my attention is that last year Maurice he was describing the transactions implemented off top of classical blockchains, and it's really interesting to see the solution of atomic swaps incorporated inside the blockchain. So that's a neat idea from my point of view.
Yeah, that's atomic swaps. So it's exactly the paper which I think Maurice presented some time ago, maybe 2 years ago, and last year he was talking about atomic deals. I think that was the extension of this work across
Hello.
multiple blockchains. Okay, yeah, Jing, hi,
Yeah.
welcome.
Hello. Welcome
Sorry,
back.
sorry. Yeah. Computer out of battery. Sorry. Am I still sharing my slides?
No, we don't see it.
Not yet.
Yes. See. Now you can see. Right?
Yeah.
Okay, cool.
Yeah, we can see it.
Okay. Sorry about that, people. Yeah, where we were, yes, about Q. Right. There are two ways you can use Q to authorize transactions. One is to include the Q script in a transaction. Then, for example, if Alice needs to pay Bob regularly, say every week or every day, but Alice wants to go on vacation too. And what she can, so she does not want to access her secret key every day to generate a signature to do a payment. So what she can do is to give Bob a piece of scripts, and Bob would include the script in transactions, and Bob would issue a transaction by himself every day. And then the blockchain would check the script and would allow Bob to make the transfer. So that's one way. Another way is to install a piece of Q scripts in accounts. And that would allow whenever a transfer happens out of this account, then the script will be validated. For example, parents want to allow kids to draw from some particular escrow accounts under some condition, say every month or some amount, then the parent can install the script in that escrow accounts and control how the tokens can be transferred. So that's layer one, smart contracts. Important thing to note is that currently Q has no side effects on the blockchain. It's a logic that will only output true or false, and true or false will decide whether the transaction happens or not. A good thing about this is that since there is no side effects, there's no states, uh, it does not cause state space explosion on the blockchain. So far, we can see that a complicated smart contract would have large state space that the layer one blockchain needs to carry through all the time, and that is very costly. But currently, Q does not have states. In the future, we do plan to install states to Q to allow to do certain state-dependent applications. But this will also be installed in a very controlled manner that only kept careful with the size and what type of states can occur in layer one. Also, stateful Q will be important part for off-chain smart contracts that that will also utilize it to finalize results on the blockchain. Okay, so that's about layer one. We have been very thoughtful about what feature to put in layer one, and when it gets to smart contracts, we look at many smart contracts applications, and we realize that not all contracts belong at layer one. In particular, what type of contracts we do not want to do in layer one? Smart contracts that are too big. For example, in private placement of security, there are typically a database of vetted investors. There may also be a database of blacklisted investors, and this database may be large, and very often they are sensitive information that people do not want to put on the blockchain. And this is something that we are not going to have it in layer 1. Sometimes smart contracts are just too slow. In particular, there are a lot of privacy-related applications, zero knowledge, private coins, homomorphic encryption, the like, and smart contract, with a lot of assertion checking. We do not want such user-defined computation to slow down the block generation for everybody. Sometimes some smart contracts are just too weird. Say CryptoKitty, CryptoKitty popped up and crashed Ethereum in 2017. It has a flavor of non-fungible token, but it's way more than a standard simple non-fungible token because it has intensive computation and it has secret formulas with randomness involved. So it is pretty computationally intense. That's part of the reason why it congested Ethereum network. It's hard to prepare for such a thing because it appears suddenly and then disappears suddenly. It would be difficult to accommodate since if it is a standard non-fungible token, that's easy to handle. But with all other add-on features, it's very hard to write a template in layer 1 for it. And there are also smart contracts that are just too complicated, probably need specialized wizards and are not for muggles. There are contracts where just be easier to do modularity, proper software engineering with higher level languages, not at assembly level. Modular decomposition. Sometimes there would be subcontracts controlled by adversaries or parties you do not trust. And it's hard to develop templates for all of them. So put them together, we see there is, even though layer 1 solutions would go a long way and support a lot of applications, we see there's a long tail of smart contracts that we do not want to handle directly in layer 1. They're too big, too long, too weird, too complex, and so on. And those are the contracts that we're going to handle in off-chain. And the approach, I think we do not have time to dive into it. So I'm going to give you the principles and some key ideas here. The principle is to move the long tail of user-defined computation out of the blockchain's critical path and keep block generation fast and lightweighted, so that a user who only want to make a transfer or only want to do an atomic swap do not need to land up at the VM side and can be very quickly processed in the consensus protocol. And the layer 2, the off-chain virtual machine will do the heavy lifting for all other computations. And the computations will come back to layer 1. So this is one thing. As I said, consensus and the smart contracts are two big things of blockchain, but they do not need to be mixed up altogether. That we want to separate the consensus from the VM so that consensus protocol does not run a full-fledged VM. We also do not want the VM to run a separate consensus again. So the VM will utilize the main blockchain to achieve consensus for the results. And what that gives us is that the VM, since it does not need to achieve consensus, it has a much smaller committee that would be enough to ensure correctness. And as mentioned before, atomic transactions until will be used to enforce the state transition, since a smart contract call may have multiple effects touching multiple accounts. A lot of problems were caused in smart contract applications before that automaticity is broken. Some status transfer has already happened and some others are blocked. In our system, this would not happen because we are going to enforce that in layer one, what automaticity we want to achieve. So that's our principle for the off-chain approach. In terms of language and VM, I would say that we have a big flexibility here. It's pretty much whatever we want and whatever user wants within reason, of course. Because the off-chain approach gives us great flexibility. The architecture itself is pretty much VM agnostic. We can plug in whatever VM we like, and then the blockchain does not really need to be aware of that. But what kind of language that we want? We want a few things. First of all, I think there is a rich literature in the programming language domain that has many proposals for designing better programming languages for blockchain, and all of them have good features built in it. And this is something converging in the literature. We see a lot of common features popping up in terms of how a smart contract language should look like. In terms of our solution, our language would like to be, human readable with modular structure. We're going to have it interpreted rather than having a compiler because that's another set of software that we will have to trust. But without the compiler, we will have a smaller trust base. Strongly typed, sufficient sanity checks. For example, money will not be created out of nowhere and will not disappear into thin air, and other built-in security features as well. Static dependency, no dynamic dispatch, indefinite loop or recursion will not be allowed in the system, and so on. So in general, this is a very, very big project that we have been working on ever since last year with myself and my colleagues with Maurice Herlihy, with Luba and Victor. Quite several people are contributing to this project, and we are now carrying it through to the next stage of deployment. So we'll let people know when we are ready to release it as a product. All right. So I think we are out of time as well. So this is all I want to tell you. And this is really, we just passed our mainnet launch anniversary. There are a lot of things happened last year, but I would always say that this is just the beginning because we have a lot of things in our mind that we would like to do. For developers, we have all the code open sourced, and you can go to the developer forum to get documents, tutorials, examples, and the GitHub repo, and etc. And for people interested in recent developments, you can find them in our news sites and our social media. Very last thing. For people who are interested in those type of puzzles, we put a puzzle in our Genesis blog when we launched. So have fun and take a look. Thanks.
Thank
Well,
you. That was
thank
a
you.
really great talk.
So let's check if there are questions.
In the meanwhile, I have a question on my side, not related to the partition tolerance. That's like a doomed word today. So the question about the programming language, if you permit. So do you support only deterministic opcodes or operations inside this language, or do you allow any sort of non-determinism inside the language? Could you comment on that?
Oh, currently, no. Currently, well, there are different stages. The first stage, it will not be allowed. that, for example, the length of the arrays will be prefixed, and there will only be very simple, like for maps, folding and the filter operations. So the first stage is, the answer is no. After that, we would install extensions starting doing that, but will be in a very careful way.
I see. Thanks.
I have a quick question again on the system model behind the Algorand self-selection protocol. So in the self-selection, you use hashing for choosing yourself for participating in the lottery. So do you assume that the computational resources used for hashing are more or less fairly distributed?
Hashing is very cheap computation. Like hashing and inversing hashing is very different. Hashing itself would take something like milliseconds, something like that.
Yeah, but
Uh,
you keep trying and trying and trying, right? So if you have a very
that's the point. That's the point of unique signature.
Mhm.
That's where I mentioned that, yes, the point is that in our system, it does not help you. You keep on trying different inputs to the hash.
Okay. So there's a question coming. Yeah, there is a considerable lag between you talking and the what the users see. So that's why we should wait for a few seconds before we get a reaction from
Sure,
student.
sure, yeah. I think I don't know how the students are distributed. Are they all in St. Petersburg?
No. It's all around the world.
That's what I thought. Yeah, I think there should be considerable delay crossing the internet. Yeah.
No, it's also the projection system is built in such a way that it first captures the video and sound and then sends it to the students. And there's
Oh,
some
I
process.
see.
Okay. So the question is, yeah, what kind of currencies Algorand supports? So does it support multiple currencies in the implementation of proof of stake?
In proof of stake, the only currency allowed is our native algo.
Okay.
In terms of layer one currencies, there are many you can use: USDT, USDC, and so on.
Okay.
Yeah, I believe we're running out of time, so we can move all the other questions to the discussion room.
Yeah. I suggest we start at 6:45 Moscow time in 15 minutes.
In 15
Yeah,
minutes.
we'll have a very short closing now, and then we'll resume with you in Zoom webinar, and you should receive the link.
Sounds good.
Okay, well, thank you very much.
Thank you very much once again.
Thank you. Talk to you later.
Yeah, and please don't leave. I'm addressing the students, so you can leave. You can take your break and have some coffee.
See you.